Now we want to discuss the limitation of valence shell electron pair repulsion theory. Okay, in the last class we discussed about the shape using valence shell electron pair repulsion theory. Now the limitations. Okay, so limitations of valence shell electron pair repulsion theory, which means VSEPR theory, the limitation. Okay, the first limitation, that is multiple bond treated as single bond. Here the multiple bond which is treated as what? Single bond. That is the first limitation. Okay, we already seen that in your SO2 molecule, right? SO2 actually have two bond pair and a lone pair, but two bond pair means actually a bond pair is treated as a double bond here, which means a multiple bond is usually treated as single bond in case of VSEPR theory. Okay, the second limitation, there are a few limitations only. The second limitation, VSEPR theory is able to explain the geometry, right? But it is not able to explain how a bond is formed. Okay, not explain how a chemical bond formed. How a chemical bond formed. Okay, so these all are the main limitations of valence shell electron pair repulsion theory, and we know that VSEPR theory, which is introduced by Sidgwick and Powell. VSEPR theory introduced by Sidgwick and Powell, which later modified by Nyholm and Gillespie. I already discussed the term Nyholm and Gillespie in the first. Now actually the VSEPR theory introduced by Sidgwick and Powell and modified by Nyholm and Gillespie. Okay, so let me move to the next idea. That is the idea or the next theory, that is actually for explaining how the bonds are formed. Okay, the theory is valence bond theory. Valence bond theory. Okay, a theory that based on quantum mechanical concept. Okay, valence bond theory based on quantum mechanical concept of atom. Okay, valence bond theory, VBT. Ready? Actually the valence bond theory proposed by Hitler and London. Proposed by Hitler and London. Okay, there are actually two main concepts here for valence bond theory, and the first concept, that is atomic orbital overlapping. What? Atomic orbital overlapping. Atomic orbital overlapping is the first concept, and the second concept, that is hybridization. Okay, so first of all we have to discuss what is atomic orbital overlapping. Actually the bonds are formed by the overlapping of atomic orbitals. Okay, for example in your Ncert they explain the formation of hydrogen molecule. That explains the formation of hydrogen molecule. Listen, we have two hydrogen atoms, H and H. They combine to form the molecule H2. Okay, wait, let this be the hydrogen with an initial A, this be the hydrogen with an initial B. Ready? So let me consider the two hydrogen atoms. Hydrogen with a nucleus of one positive charge and electron, and this is the electron of the atom A. Electron of atom A. Like that, there is the hydrogen B with an electron EB. But the nucleus of this hydrogen, let it be Na with a positive charge, and this one is Nb. If these two atoms are in an infinite distance, when they come closer, at a particular distance, they make a bond. Okay. So that is actually the bond formation concept. So let me introduce that with the potential energy versus internuclear curve. This is the internuclear distance. R is the internuclear distance, and here is the potential energy. And here the potential energy 0. Here the potential energy negative. Here the potential energy positive. Okay. So this particular distance is the R. Okay. When the two atoms are in an infinite distance, there is a small kind of attraction. Okay. And that is the old attractive force. Old attractive force. When the two atoms are in an infinite distance, there is a chance for a small kind of attraction, and that is always, there is a universal attraction. That means attraction between electron of that atom to the proton of that typical atom. So there is an attraction between Ea and Na, as well as Eb and Nb. Ready? Then we all know. Since there is an attraction, at infinite distance, there is a small negative potential energy for atom, or for there is a small potential energy at an infinite distance. So that's a potential energy, attractive energy, which means the potential energy is negative. Okay. Now, when they came closer, okay, when they come closer, what happened? New forces are developed. And the new forces are, that may be attractive force or it may be the repulsive force. What are the new attractive force? When these two come closer, what happens? There may be a chance for the attraction of electron of this atom to the nucleus of another atom, and electron of this atom to the nucleus of this one. Oppositely charged attraction. So which means Ea may attract with the Nb if and only if they come closer. Ready? And Eb may attract with the Na. And there is a chance for repulsion when they came closer. Electron repulsion, nucleus repulsion. So there is two kind of repulsion also. Ea, Eb repulsion, as well as Na, Nb repulsion also. Na, Nb repulsion also. Ready? Is it okay? Fine. Ea, Eb repulsion and Na, Nb repulsion. Ready? So when they come closer, there is a competition between this attractive force and repulsive force. Okay. So initially, in a particular distance, when they come closer, the distance are relatively higher. When they come more closer, the distance decreases. So if you are moving from left to right, means from here to here means the distance decreased. Okay, distance between the atoms decreased. Ready? So at an infinite distance or the maximum distance, there is a potential attractive force. So the potential energy is negative. But they when came closer, initially attractive force dominate. But in a particular distance, attractive force will be equal to repulsive force. Hence the plot will be like this. So up to this barrier, in a maximum distance or in a greater distance, attractive force is greater than what? Repulsive force. That's why the potential energy decreased. At a particular distance, attractive force is equal to repulsive force. Okay. If that particular distance exceeds, which means when the two atoms are more closer, then there is a chance for greater repulsion between these two. So repulsion dominates. So when distance decreases, repulsion dominates over attraction. That's why the potential energy increases. So this is a curve. Okay. So the state where there is a balanced equilibrium, there is a balanced equilibrium when the attractive force is equal to repulsive force, there is an equilibrium, and that equilibrium state there is no movement of the atoms because attraction repulsions are balanced, and that particular state, that state is said to be bonded state. That particular state, the state is said to be bonded state. Ready? That particular state is said to be bonded state. Okay, so what is bonded state? Bonded state, or this is how the bonds are formed. Okay, bonded state where F attractive equal or F attractive that balance F repulsive. Okay, and in that state, what is the internuclear distance between the atoms? What is the internuclear distance between atoms? In that state, in bonded state, the terms are only in bonded state. In a bonded state, the internuclear distance is of that two atoms is defined as what? Bond length. Okay. And in that particular stable state, there is a release of greater amount of energy actually. Nearly 435.8 kilojoule per mole. Nearly that much energy released by hydrogen. That is a bond energy actually. Where the distance between two nuclei in that particular bonded state is 74 picometer for hydrogen. That means in the case of hydrogen, the bond length is 74 picometer. Okay. So in that particular comfortable stable state, when there is a stable state, there occurs a stable state of F attractive equal to F repulsive. The decreased attractive force releases a attractive force decreased, and decreased attractive force releases a energy, and that energy which released in that particular bonded state is defined as energy released in that particular state is defined as bond energy. What it is? Bond energy. Okay. And in your Ncert textbook, actually there explains the bond formation of hydrogen. Okay. So the bond length for what? For hydrogen, that is 74 picometer, and bond energy for hydrogen, that is nearly 435.8 kilojoule per mole. Since it is released, the magnitude will be minus. Okay, ready? Fine. And one more point is the, listen, in that particular state, that is a very important point. In here or in bonded state, the atomic orbital, actually how the bond is formed means when your hydrogens are in a particular distance, which means the distance is in distance where the F attractive equal to F repulsive, which means when they are in a 74 picometer distance, atomic orbital of S at 1s orbital of hydrogen will overlap with the 1s orbital of another hydrogen. This is the 1s orbital of hydrogen A, this is the 1s orbital of hydrogen B. In that particular distance, when the distance are 74 picometer, they get overlapped. So they get overlapped to form that particular bond. So when the two atoms come closer, what happens means attractive force and repulsive force will be equal at a particular point. That point is said to be equilibrium state. And in that equilibrium state, that is said to be bonded state, and in that equilibrium state, the atomic orbital, here the atomic orbital of atom get overlapped. In that particular state, the atomic orbital of atom get overlapped. Ready? Fine. Atomic orbitals of atoms get overlapped. So this is how actually a bond formed, and it is explained on the basis of valence bond theory. So now we can discuss how the atomic orbitals can overlap and what are the criteria, what are the different types of overlapping like that. Okay, so move to the next. atomic orbital overlapping. Atomic orbital overlapping. Okay, now we want to discuss the criteria or the how overlappings are possible, right? Okay. Ready? Listen. Overlapping theory. So read from here. The main postulates of atomic orbital overlapping. To form a covalent bond, overlapping occur between two half-filled valence electron of two atoms. Yes. To form a covalent bond, in order to form a covalent bond, there should be the overlapping of atomic orbital, but it should be between half-filled valence shell orbitals of two atoms. Okay. The combining orbitals of two atoms should be halfly filled. Ready? Which means if there is a half-filled orbital of hydrogen atom like 1s1 and then another half-filled orbital of hydrogen atom like 1s1, they can form a covalent bond. Okay? Ready? The next point, resulting bond acquire a pair of electron with opposite spin. Yeah. If these two are overlapped, then there forms a resulting bond. Okay, and the bond have a pair of electron in the opposite spin. So overlapping half-filled overlapping valence electron. Overlapping occur between half-filled valence shell orbitals with and these the half-filled valence shell orbitals where the electron should be in opposite spin with the opposite spin electron. Okay, opposite spin electrons. Ready? So that's the second point. Second point, resulting bond acquire a pair of electron with opposite spin, like that. Okay. What about the third point? Orbital come closer to each other from the direction and there is a maximum overlap. When there is a bond formation, the orbitals are come closer. We know that. In a particular state only the overlapping possible, right? Well, that particular state, the peculiarities of attractive force is equal to F repulsive force. Fine. So orbital come closer to each other from the direction in which they maximum. Okay, in a particular, when they comes closer in a direction, then only they form a maximum overlapping. So every covalent bond have a directional property because that is a covalent bond is formed by the overlapping of particularly oriented orbitals. We know that orbitals have a particular orientation in space. When they overlapped means there will be a particular orientation of that typical bonds. So all covalent bond have a direction. Ready? The next is extent of overlapping. Extent of overlapping means degree of overlapping. How much overlapped? Okay, overlapping, if the overlapping is like this have a greater extent of overlapping. If the overlapping is just like this, or this is not an overlapping is just like this. These two have different extent of overlapping. This have a greater extent of overlapping. That means this bond is a strong bond, where this is a weak one. Okay, so extent of overlapping, that is directly proportional to strength of chemical bond. Directly proportional to strength of the chemical bond. Is it okay? Directly proportional to strength of the chemical bond. The next, extent of overlapping proportional to strength of chemical bond, fine, and that depends on two factors. And the first factor, that is nature of orbitals. The more directional orbitals like P, D, F the more directional orbitals are the PDF, okay, with a double dumbbell shape, they can produce greater overlapping. Listen, here is a overlapping of, or let's consider the overlapping of 2p orbitals. Overlapping of 2p orbitals and also overlapping of 2s orbital. So this is the p orbital which can overlap with another p orbital which have greater extent, but when the overlapping is between 2s orbital, relatively the extent will be decreased, because p d f orbitals are directional orbital. They can overlap in a maximum extent, so that the strength of the bond will be increased. Okay, so bond strength or the extent of overlapping, that depends on two factors. The first one, how the orbitals are, what is the nature of orbital, whether it is directional or non-directional orbital. So orbitals like PDF are directional orbitals, so they can produce more or a greater extent of overlapping, which means their bonds are relatively more stronger. Where s orbital is a non-directional orbital, so they usually produce less extent of overlapping. Okay, lesser extent of overlapping. Ready? So this is the first idea, or the first criteria, that depends on the orbital overlapping. And what is the second means? Nature of overlapping. Nature of overlapping. There are two different types of overlapping. Either the overlapping may through axial overlapping along the internuclear axis. Either it may be through axis, so that is axial overlapping. We will discuss that. Or the overlapping may be by means of sidewise, lateral overlapping. Okay. If there is an axial overlapping, the extent of overlapping is more. The formed extent of overlapping will be more. And we know that such kind of bonds are said to be, the bonds formed by that type of overlapping is called sigma bond. Okay, so there are two possibilities for the overlap, either through the axis, either between the axis, so there is a more overlapped or more extended bond formed, or it be by a lateral pattern, side to side, so relatively lesser extent will be there. Okay, so order of strength of coaxial bond, which means when the overlapping is around axis, then which have greater order of strength means the overlapping between PZ have greater extent. And this is overlapping between two PZ. This is a PZ, the other PZ. Okay. Which have greater extent than SPZ. This is a PZ orbital, you know what is a PZ orbital, and this is S orbital. Which have greater extent than SS orbital. Okay. So this is the order. Ready? Move to the next. As the value of N increases, bond strength decreases. The bond strength between 1s and 1s is greater than 1s and 2s. That's greater than 1s and 3s. As the value of N increases, N value increases, relatively size increases, bond extent decreases. As the value of N increases, bond strength decreases. Here the value of N is 2p. 2p. I'm sorry, 2p. Where all are same here, but here the N value 1, N value 2, N value 3. So as the N increases, bond strength decreases. Ready? But if N is same, then PZ have greater extent than PS, PZS and SS. That is exactly given here. If the N is same, PZ have greater than SPZ than SS. Okay. And the last few points, that is, electron in which is already paired in a valence shell can either enter into a bond formation. Electron which is already paired in the valence shell can either enter into bond formation if they can be unpaired first and shifted to vacant orbital of slightly and higher energy of the same energy. Okay, so which means that if there is any kind of paired electron, they can excite it to the higher orbital so that they can form the bond. That is exactly discussed in hybridization. Okay, we will discuss it using the structure. And this point explains how the trivalency of boron, the trivalency of carbon, pentavalency of phosphorus. Right. We will discuss that. Okay. We will discuss the orbital diagram of hybridization of each molecule. Then we will be okay with this point. Ready? We will be okay with this point. Okay. The last points are, there are two types of bonds. Sigma bond and pi. Three types of bonds. Sigma bond, pi bond and delta bond. Delta bond is not common, but sigma and pi bonds are very common. Okay. So let's discuss the sigma bond. Formation of sigma bond and pi bond. Okay. Formation of sigma bond. Sigma bond may be formed when there is an orbital overlapping between S and S, S plus PZ, PZ plus PZ, etc. Okay, because sigma bond is formed when the overlapping is along internuclear axis. Okay, listen. If I am considering internuclear axis as Z axis, let Z axis, internuclear axis. Let Z axis is the internuclear axis. This is the internuclear axis. Then how the overlapping between two s orbital will be like this. These are two s orbital. If this is the internuclear axis, one s orbital here, another s orbital here. So they may overlap in an end-to-end pattern, or they may be overlapped like this. So this is the SS overlapping. And what are the speciality of this SS overlapping? This is axial overlapping. Since this is an axial overlapping, the bond formed is a sigma bond. Okay, I'll give you example here. So by means of SS overlapping, there forms a sigma bond. Okay, I'll give you example here. Listen, example. I have two hydrogen of 1s1 plus another hydrogen of 1s1. If they get overlapped, there forms SS overlapping, and we all know that when they get overlapped, there forms a bond, single bond. This is an SS overlapping, right? Yes. There forms a single bond, and that single bond should be a sigma bond because the overlapping is end-to-end overlapping. That single bond will be a sigma bond. Ready? Fine. So now what about the overlapping between S and PZ? S and PZ. S-PZ overlapping. So let me extend here. S-PZ overlapping. This is the S orbital of an atom. If this is the internuclear axis, Z axis, the axis which is passing through the nucleus of two atoms, Z axis. Usually the internuclear axis are Z axis. Then we know the shape of PZ. PZ is actually along the internuclear axis, right? So when this S and PZ are overlapped, the overlapped structure will be like this. And this is the SPZ overlapped structure. So this SPZ overlapping is actually along the internuclear axis. So here the formed bond is a sigma bond. Okay, I'll give you an example for that. Let's consider HF, H plus F. What about hydrogen? Hydrogen is 1s1. What about fluorine? Fluorine is 1s2, 2s2, 2p5. 2p5 is actually like this. So this is the 2pz. So if this electron is like this, okay, so there is a chance for the overlapping between these two. which leads to the formation, or which is said to be sp-z overlapping. And from that sp-z overlapping, there is a chance for the formation of a bond, single bond, and that bond should be a sigma bond, because the single bond between H and F is between S and PZ, so that is a sigma bond. Okay, ready? Fine. There is one more chance for your sigma bond. The very same internuclear axis, let me extend that, very same internuclear axis. Okay, if that internuclear axis have 2 pz orbital, this is a pz orbital which can overlap with another pz orbital. This is with the 1 electron, this is also with the electron. Okay, so what is the speciality? When these two get overlapped, there is a greater extended overlapping formed. So a greater extended overlapping formed. That's why. And this is said to be the pz-pz overlapping. Okay, so we can see the pz-pz sigma bond in the case of fluorine, FF. Fluorine with an electronic configuration 1s2, 2s2, 2p, 2pz. This is a pz. Or what about the next fluorine? 1s2, 2s2. Also have a 2pz, 2pz. When these two unpaired electrodes get overlapped, there is a pz-pz overlapping. And due to that overlapping, we all know that there forms a bond. That bond is F of single bond. Now, F of single bond should be a sigma bond. Okay, ready? Okay, fine. Okay, fine. Lisa. So it is very clear that usually the sigma bonds, the overlapping should be between the axes, right? Overlapping should be between the axes. If the overlapping is between the axes, either the overlapping may be SS, or it is SPZ, or it is PZPZ. Okay, in which the more extended overlapping is between PZ, and that will be greater than SPZ, and that is much greater than SS. Okay, fine. So we want to discuss the next, that is, if n is same, this is a extent of overlapping. Okay, so we want to discuss the next, that is pi bond and delta bond formation, and a comparison between sigma bond and pi bond. Okay, followed by the hybridization.